Welcome to today's Explainer. We're diving headfirst into one of the most mind-bending, absolutely fascinating attempts to understand the literal building blocks of our reality. I'm so excited to get into this with you today because we're looking at a topic that has just completely captivated and honestly frustrated the greatest minds in physics for decades. Yep, we are talking about string theory. Let's kick things off with a kind of provocative thought. What if everything around us, from the screen you're staring at right now to the furthest stars in the galaxy, what if none of it is made of tiny solid dots? What if instead it's all made of invisible, vibrating musical strings? Just imagine it, the universe essentially playing this continuous cosmic symphony. It's a gorgeous concept, right? But to understand how physicists actually arrived at this wild idea, we need to retrace their steps. To make sense of this whole cosmic puzzle, here's our roadmap for today. We're going to hit 6 key areas: the ultimate physics dilemma, what is string theory, the cosmic symphony, dimensions and M-theory, cosmic strings and limitations, and finally, the bootstrap breakthrough. All right, let's jump right in. Part 1. The ultimate physics dilemma. Basically, the monumental roadblock that started it all. So, we've got Einstein's general relativity, right? It flawlessly controls the massive stuff. We're talking galaxies, stars, planets. It describes gravity as this incredibly elegant warping of space-time. But then on the flip side, we have quantum mechanics, and that rules the microscopic realm, subatomic particles governed by wild probabilities and this chaotic quantum foam. Now, both of these frameworks are absolute triumphs in their own domains. But here's the devastating problem. Mathematically, they just completely break down when you try to force them together. Like, if you try to use general relativity to calculate what's happening at the ultramicroscopic quantum level, the math just spirals out of control into these totally nonsensical infinities. It just doesn't work. Which brings us to the ultimate question. If both of these frameworks are right in their own specific realms, how in the world do we find a single unified theory of everything? Because, let's face it, we can't truly understand our universe if its two foundational rulebooks literally contradict each other. That brings us to part 2. What is string theory? Time for a radical remodel. Enter string theory. This was a massive paradigm shift. Instead of looking at elementary particles as these zero-dimensional point-like dots, this framework replaces them with one-dimensional entities, vibrating strings. The absolute game changer here is that by taking a microscopic dot and stretching it out into a tiny line, those devastating infinities that broke our math, they just suddenly vanish. Poof! When strings collide, they don't smash together at a single infinitely dense point. They actually smoothly interact and rebound. Now, to wrap your head around the scale we're talking about here, check out this number, 10 to the power of -32 meters. That is the Planck length. To put that into perspective, we are talking about an entity roughly a billion times smaller than a single proton inside an atom. It is unbelievably minuscule. But this is the exact scale where quantum gravity takes over and where these strings are theorized to exist. And these aren't your ordinary guitar strings either. We're talking about the weird, wild physics of relativistic strings. Unlike a normal rubber band, a fundamental string is characterized entirely by its tension alone. Its endpoints are literally moving at the speed of light. And because we're dealing with relativistic physics here, energy and mass are interchangeable. So simply stretching one of these strings out actually creates mass out of pure energy. It's a fundamental rethinking of how matter even exists in the first place. All right, moving on to part 3, the cosmic symphony, or how matter comes from vibrations. Now, you might be wondering, if absolutely everything is made of the exact same type of string, how do we get so many different particles? Quarks, electrons, photons? Well, think of it like a violin. These strings represent different vibrational modes. Just like how plucking a violin string creates a fundamental tone along with various overtones depending on how it vibrates, a fundamental string in physics acts like a cosmic symphony. The specific way a string twists, folds, and vibrates literally determines its mass and its charge. That vibration manifests as actual, distinct physical matter and energy. How cool is that? And the shape of the string matters too. Strings can be open, having 2 ends, or closed off into a loop. If an open string vibrates in a specific way, it gives us a photon. That's the carrier of light and the electromagnetic force. But if a closed string loop vibrates, it gives us the graviton. That's the hypothetical quantum particle that regulates gravity. This is huge. For the very first time, all matter and all force carriers, including gravity, are arising from the exact same mechanism, the quantum fluctuations of these relativistic strings. General relativity and quantum mechanics are finally playing the exact same instrument. So let's jump into part 4, dimensions and M theory, where we literally have to rethink space itself. So physics had this massive breakthrough, right? But then it ran into a really bizarre problem. As theorists dug deeper into the math, they didn't just find one string theory. They found 5. You had type I, type 2a, type 2b, and 2 heterotic theories. And for a long time, the physics community was just completely stuck. All 5 of these were mathematically perfect, but they were distinct from one another, so nobody knew which one actually described our reality. It was literally like having 5 completely different maps that all claimed to lead to the exact same treasure. But then 1995 rolls around and brings a massive paradigm shift. Physicist Edward Witten comes along and unites all 5 frameworks with something he called M theory. He proved they weren't actually competing theories at all. They were just different limiting cases, like different reflections of one single master theory. But there was a catch. To make the math of M theory actually work out, the universe has to contain 11 dimensions. Yeah, 10 of space and 1 of time. Oh, and it also introduced branes, so 2-dimensional membranes and higher dimensional entities, not just those 1D strings. Which naturally leads us to part 5, cosmic strings and limitations. We gotta look at the predictions, but also the serious hurdles. Let's say massive, macroscopic cosmic strings left over from the early universe actually still exist today. They would act incredibly strangely. Unlike a planet or a star, they wouldn't just pull objects toward them. Instead, they would warp space-time so intensely that they create what's called a conical singularity. Basically, if one of these giant strings passed between us and, say, a distant quasar, it would act like a perfect gravitational lens. It would literally duplicate the image of that distant galaxy right in our telescopes. Now, we haven't actually spotted one yet, but this at least gives us a real physical phenomenon to hunt for out in the cosmos. Now, despite all this mathematical elegance, we've got to be totally impartial here and point out the severe limitations. First off, string theory currently totally fails to explain dark matter and dark energy, which, by the way, make up about 95% of our universe. That's a pretty massive gap. Plus, the math predicts an almost infinite landscape of multiple universes, which makes it incredibly hard to pin down predictions for our specific universe. It also really struggles to integrate the observer dependence principle of quantum mechanics. But the absolute biggest hurdle? To prove this directly, we need to smash particles together at the Planck scale. And to do that, we would literally need a particle collider roughly the size of a galaxy. So, yeah, not happening anytime soon. But don't lose hope. Let's hit our final section, part 6, the bootstrap breakthrough, a brand new mathematical path. Okay, so since we obviously can't build a galaxy-sized collider, researchers at Caltech recently tried something totally different. They used an old concept called the bootstrap method, but updated it with modern mathematical tools. Honestly, it's kind of like solving a cosmic Sudoku puzzle. Instead of starting out by just assuming string theory is true, they set some incredibly simple, broad rules for how particles should logically behave at extreme energies. They assumed ultrasoftness, which just means particles interact smoothly without the math breaking into those nasty infinities we talked about earlier, and another rule called minimal zeros. And here is the crazy part. When they solved the equations based only on those super simple logical assumptions, the exact mathematical signatures of string theory appeared entirely on their own. No way, right? This absolutely mind-blowing moment is summed up perfectly by Caltech physicist Clifford Chung. He said, "The strings just fell out." They didn't force the math. They didn't try to make strings happen, but the solution naturally contained the precise infinite tower of massive spinning particles, the harmonics, that string theory is totally famous for. It was a completely independent mathematical path using totally different starting rules that somehow miraculously led to the exact same destination. Which leaves us with this final, truly profound thought to ponder as we wrap up today's explainer. Even if we don't have the technology right now to build a microscope or a collider large enough to directly see these microscopic vibrating threads, does this sheer mathematical inevitability mean something deeper? Does the universe at its most fundamental bedrock level secretly want string theory to exist? Are we really, truly all part of a beautifully complex 11-dimensional cosmic symphony? It's a question that is absolutely going to drive the next generation of physics. And I really hope this explainer helped you hear the music just a little bit clearer.